Okay, so there's our expression. So let's go ahead and try to solve this. So here I rewrote the expression at the top, and we'll actually just go through the steps of solving this. All right, so first thing is we need a rate equation to relate Q dot to temperature. So what's our rate equation? It's going to be Fourier's law. Okay, so Fourier's law for this in radial coordinates is going to be minus K times the cross-sectional area, right? Cross-sectional area available for heat flow. So that's 2 pi r times L times dt dr. That's our Fourier's law rate equation for cylindrical coordinates. All right, so I'm going to substitute that back in up here, and we have then ddr of this whole thing minus k times 2 pi r L dt dr is equal to our right-hand side, so 2 pi r L g dot triple prime. Okay, I can now cancel out anything that's constant from this. So let's see, I can cancel out 2 pi. I can cancel out L. And I'm left with D. So actually, this is an important thing to point out. So normally when we write these things in what we call like a standard form, you're going to divide out everything you possibly can from the highest order derivative and put it elsewhere in the equation. And so the step you're trying to get to is highest order thing clean by itself, constants and everything else on other terms. So we'll divide out anything that has to do, that's on the highest order derivative. So let's do that, and we end up with this. We say dr, right? We can divide out minus k. We cannot divide out r, because we're taking the derivative with respect to r. So r has to remain in there, right? R is not a constant. Okay, so we end up with r dt dr here. And that's equal to, on the right-hand side, we have now minus r times g dot triple prime divided by k. All right, there's our ODE in terms of temperature. So our job now is to solve this ODE for temperature, come up with an expression for temperature. Okay, any questions on what we've done here so far? We good? Okay, so how do we solve this for temperature? Well, this one, if we look at the right-hand side, we have something that's a function of r on the right-hand side. And we have a differential of a term. So what we can actually do is bring this dr over here over to this side and just say, okay, this differential of r dt dr is equal to minus r g dot triple prime over k dr. Okay, now we can integrate this. Right? Let's just integrate both sides. So let's integrate this side, integrate this side. So integral of a differential on the left is just that term. We just get the term back, r dt dr. And on the right-hand side, we have the integral of minus r times some constant stuff. Okay, so here we end up with, right, so we'll see minus g dot triple prime times r squared divided by 2, right? So 2 times k plus a constant of integration. So good. I mean, we've made progress here. And we can see now actually we can separate the variables, right? This equation is separable and we can solve it that way. It might be the case in future analyses that we're doing that you're going to try this. We get to a certain point here where it's not separable, you can't solve it. Then we have to use different techniques. For this stuff we're talking about so far, up to this point at least, so that it's separable and we can solve it this way. Okay, so what do I do next? So I'm going to start writing up here again. So I'm going to bring r over to the right-hand side and dr over to the right-hand side. So I'm left with dt is equal to minus g dot triple prime. I'm going to divide the right-hand side by r, so that just leaves r there, over 2k, plus c1 over r, all of that times dr. Okay, let me just write it this way, all of this times dr. So now I can integrate again, right? integrate one more time, and I'm left with integral of this, integral of this. So now I have an expression for t, right? T, which is a function of r. And that's equal to what? So that's equal to minus g dot triple prime, right? Integral of r is r squared over 2, so that becomes over 4k, plus c1 times, what's the integral of 1 over r? ln of r, natural log, plus another constant of integration. Right, so I just come up with a general solution for temperature in this in this conducting body that includes generation. Right? Make sure that makes sense to you. One thing to point out is, if you've seen this before, you maybe recognize this, but this equation here, that's the same thing we derived before, right? C1 ln of r plus C2. That was exactly the same thing we derived before when we did this for cylindrical coordinates without generation. But now we've got a generation term here. So in fact, what we're doing is we're taking a steady state, a 1D steady state solution with no generation, and we're adding to that a profile that has to do with the amount of generation that you have, right? So you're kind of layering these things on top of each other, right? And it just works out to be this. Okay, so continuing on, next step, we have to enforce our boundary conditions. So up there, again, I've got what we just solved. Hopefully that's the same thing. So we have to enforce some boundary conditions. So think about, first of all, where, what do we mean boundary conditions? Which domain? We're talking about the R domain. So we need boundaries that correspond to the edges of the R domain. Okay, the first boundary condition is at what? R equals 0. You can't go to negative R. So our first boundary condition is going to be at R equals 0. So it's a little hard to see. Okay, so we just redraw our hay bale and put at R equals 0 this tiny little dot of a control surface. All right, so what's the difference between a control volume and a control surface? The control volume has volume associated with it. It has a differential thickness. The control surface is just a plane in space at which we're evaluating heat transfer across that plane. Okay, so typically what we'll do for a control surface is we'll draw that surface. On the left-hand side of the surface, let's see what's happening there. Maybe it's conduction, right? So on the left-hand side of that, if there's conduction, we would write a rate equation for conduction, and then that would have to be equal to what's happening on the right-hand side. Okay, if there's conduction on the right-hand side, then those would have to equal each other, right? If there's convection, then you'd say, conduction equations equaling a convection rate equation. But at that boundary, the energy has to balance, okay, at that surface. Okay, so as a bit of an aside, but here we're drawing a control surface that's infinitely small, like this little point, this pinhole surface right at the center of this of the hay bale. So at that point, can we have any heat transfer across it? Right? Well, the clue's right here. It says 0. Right? Q dot R equals 0. So no, it's infinitely small. There's no energy generation. There's no magic place that heat's coming from. So Q dot at that boundary is going to be equal to 0. Okay, so our first boundary condition, we would write that as Q dot at R equals 0 is equal to 0. Okay. Okay, now we need to, again, use our rate equation. So we are evaluating Q dot. So let's see. So Q dot is going to be, So if we use Fourier's law for Q dot, we're going to say minus K 2 pi R L dt dr. That's Q dot. We're evaluating this at R equals 0. That has to equal 0. Okay, we can divide out by 2 pi. We can divide out our minus K. We can divide out L. And then we're just saying R times dt dr. Evaluated at R equals 0 is equal to 0. Those are equivalent statements. So what do we do now? Okay, we have this evaluate at R equals 0. So I could plug that in over here, and I would say 0 times dt dr is equal to 0. All right, that's kind of helpful, but not, not really, but it actually gives us the boundary condition if you stop and think about it. So this is true under all conditions except for one, right? It doesn't matter what dTdr is. It can be any finite value, but it has to be a finite value for this to be true. So if we said dTdr is infinity, in which case it's basically undefined, then we have a nonsense equation, and it can't be useful. So the only requirement for this boundary condition is that dTdr is finite, right? That it's not infinite. Okay, so how do we actually use that? Well, let's plug in our expression for temperature that we just derived up here into this equation and see where that goes. Okay, so dTdr, if we evaluate dTdr, the derivative of that equation up there, that's going to be equal to minus g dot triple prime times r over 2k. That was kind of one of the intermediate steps. Okay, so now if we plug in this, where we are evaluating this all at r equals 0, where we say dt dr equals, sorry, I missed the term here. C1 over r, right? Don't want to forget that. So let's plug in now, again, where r equals 0. So we say, okay, minus g dot triple prime times 0 over 2k plus C1 over r is 0, right? That's equal to dTdr. So this is the crucial part. Okay, so we've now said this term goes away here, and we're left with C1 over 0 is dTdr. But we just decided that in order for this equation just immediately above it to hold, dTdr has to be finite, right? It can't be infinite. What we just wrote gives us infinity. So what's the only thing that we can do to resolve this problem? C1 equals 0, right? So C1 has to equal 0. All right, it's a bit of, yeah, it's confusing, I think, but if you sit there and think about it long enough, you can probably convince yourself C1 has to be 0 is the outcome of this boundary condition. Okay, yeah, question? So I would think about this in terms of taking the limit as r goes to 0, right? So in the limit that r goes to 0, we have to have this enforced. Okay, any other questions? Okay, so the outcome of this boundary condition is C1 equals 0. Good, we got that far. So what's the other boundary condition? Hopefully that's a little bit easier. Let's see, let's follow my notes here. Okay, so the other boundary condition, again, we're going to draw a control surface. We've drawn a control surface out here, right at the edge of the domain that we're trying to model. Note that we drew it at the edge of the hay bale and not on the outside of the plastic. Okay, so we're in this exercise, we're specifically developing a temperature model within the hay bale. And we're treating everything outside the hay bale as, let's say, boundary conditions or externalities, right? Those are things that are outside of the temperature equation that we're trying to derive. So don't get confused about the fact that there's still stuff going on in the r direction. We're only developing a model for the hay bale, right? Within r equals 0 to r equals r bale. That's what we're doing. So then our boundary condition has to be consistent with what's happening at the boundary between the bale and the plastic. Okay, so that's where we draw our little surface. Right? So we draw our surface, come on, zoom in. So we draw our surface right here. It's kind of drawn with 2 lines, but really what it is just a single line right at that surface. So again, like I said before, let's think about what's happening immediately to the left and within the domain and write a rate equation for that. And then we're going to write a rate equation for what's happening on the other side of that surface. Okay. So let's see, on the left-hand side. All right, so on the left-hand side, we have Q dot at r equals r bale. This is a conduction Q dot, right? This is Q dot conduction at r equals r bale on the left-hand side of this surface. On the right-hand side, we have, let's just call it Q dot out. Okay, and so let's come up with expressions for each of these. So conduction, and then what's happening on the right-hand side. Okay, first for conduction. So we just decided, right up here, dt dr is this. So if we write out our rate equation for the left-hand side, that's going to be minus k 2 pi r times L times dt dr, Fourier's law, right, conduction. This is all evaluated at R equals R Bale, right? And then on the right-hand side, what do we do with this? Well, we don't have any thermal generation occurring within the plastic, and then we have convection. So we can actually model this using a resistance network. And so our right-hand boundary condition, the rate equation for that can just be a resistance network representation. So we could write this as what? So T, the temperature at R equals R Bale. All right, that's the temperature right at that surface, minus T infinity, divided by the two resistances in series. Okay, R conduction in the plastic plus R convection, right? So let's get some resistances here. So R conduction plastic, that's cylindrical coordinates. So that would just be what? That's the natural log of the outer radius, which is R Bale plus the thickness of the plastic plus thickness P divided by the radius of the bale. So it's a little messy. It's a natural log of R out over R in divided by what? 2 pi times conductivity of the plastic times L. Right, that's our cylindrical coordinates resistance, very messily written for the plastic. By the way, like the plastic is so thin, you could very legitimately use a plain wall resistance for that and get the same answer. Okay. Just as an aside. Okay, so then the convection resistance, let's see, our convection, that's going to be our convection. Let's see if I can fit it in here. So that's just 1 over H bar times the area. What's the area? Well, it's 2 pi times R Bale plus the thickness of the plastic times L. Okay. Sorry. These are separate equations. Okay, so we have those two resistances and we can plug that in. What do we do for this TR up here, right? This guy up here? Or what is that actually? What are we saying? We're saying, let's take our expression for T, the thing up in the right-hand corner, G dot triple prime R squared over 4K plus C2. Substitute that equation in there, evaluate that equation at R equals R Bale, evaluate the left-hand side at R equals R Bale, and then that's our boundary condition equation, right? So if we do that, just skip some algebra for you, we end up with pi G dot triple prime. On the left-hand side, R Bale squared times L. On the right-hand side, we have then minus G dot triple prime R Bale squared divided by 4K plus C2 plus T infinity, and all of that divided by R conduction P plus R convection. Okay, so that's our boundary condition expression. Right, and notice what we have, right? We only now in this equation have C2 appearing. So this equation could be solved explicitly for C2, gives us our coefficient, plug that back into our temperature expression, and we're good to go, right? In fact, you could just take this, write it as it is in ease, use ease to solve for C2, and then have your temperature expression done. So at this point, we're basically done, right? There's really not much else for this that we need to do.